All right, so we're going to talk about Dijkstra's shortest path first algorithm, or at least the idea of it. Okay, so one of the classic graph problems is to find the shortest path between two vertices, right? You probably recognize this problem. Anytime you get in a car, start driving using your GPS on your smartphone to go from one place to another, it is using some form of the shortest path algorithm. And most likely, that is a variant of Dijkstra's uh, shortest path first algorithm. Now, just a little bit of history. It was invented by, I think, Edgar Dijkstra in the 50s, and he published it a few years later. Now, when I was reading about how he invented it, it was fascinating that he said he designed it in 20 minutes while he was out shopping with his fiance. He was tired. He sat down and trying to figure out this problem. The most amazing thing is not just that it's done in 20 minutes, but he did it without any pen or pen, pencil, paper. So, and according to him, it forced him to avoid all avoidable complexities, which makes this algorithm very nice in his own words. So I think this is kind of a great lesson for kind of software design and programming in general to try to keep things as simple as possible. Anyway, in his original algorithm, he finds the shortest path from a single starting vertex to a single destination. Now, there is a very common variant that finds the shortest path from a single starting vertex, but to all the vertices in the graph. So that's what we'll study. And one thing to note that it only works on graphs whose edges they have positive weight or cost. If there are negative weights, which don't make a whole lot of sense anyway, this algorithm won't work. And the basic idea is that we start obviously with at the starting vertex, and then we find the closest vertex to it, and then we find the next closest vertex, and then the next one after that, and so on and so forth, until all the vertices has been searched. So from that description, you can kind of see that it is a form of a breadth first search. And with that, I'll present to you the pseudocode for Dijkstra's shortest path first algorithm. Now, I'm not going to read through it. You should pause the video and kind of read it line by line. What I want to point out is you can really see the shadows of a breadth first search in this algorithm. So there is a list, partial paths, I call it, basically keep track of a bunch of vertices to kind of visit. And then we'll loop as long as there are things in this list. And then we remove something from the list and do some clever things with it, and finally put things back into it. So again, pause the video, read through this, and then we'll go through an example of how it works. So I'm going to demonstrate how Dijkstra's algorithm works now. This example is actually from my data structure textbook, because I just want to make sure I get it right. And so given this graph, the problem is to find the shortest path to all vertices starting from the vertex S. And as we go through it, even though Dijkstra himself did use pencil or paper, but for us mere mortals, I would advise you to get pencils and papers and then draw this as we go along. So this graph, you can see that these letters next to the circles, they're the name or the label for the vertex. And each of the vertex itself right now, it has this little infinity symbol here. It just says this is the cost to reach this vertex. And right now it's infinity because, well, we haven't found a path to it yet. So it's none of these is reachable right now. Now, to run through the Dijkstra's algorithm, we keep track of a number of informations for each of the vertex. So this is a table. Each row is a vertex. So we have 5 vertices. And for each vertex, we keep track of 3 pieces of information. The first one is, have we found the shortest path yet? And the second information keeps track of the total cost of a path to this vertex from S. Okay, so it's just a path. It's not necessarily the shortest path yet. Okay, and then finally, this column keeps track of for a path to this vertex, what is the previous vertex in this path, right? Okay, so and then we can see immediately that we can initialize this table with some information for S. So the total cost from S to S is 0, right? We should be able to get to S without going anywhere else. So now the shortest path from S to S, the previous node in that path is S itself, right? So that's just to kind of bootstrap the our whole algorithm. And the information about this vertex, we can put it in the partial path, right? Because we have a path from S to S. So this is kind of similar to bootstrapping our breadth first search. So with that, we can loop through Dijkstra's algorithm, and it goes like that. So the first thing is we look at all the paths that's in partial paths, and there is only one. We find the one path with the lowest cost, and again, there's only one, so that's this. And we know that then the shortest path for this vertex has been found, which should be obvious because, you know, the shortest path to S is through S itself with the 0 cost. So we remove this vertex from the partial paths. And the next thing we do is that for this vertex, we look at all the outgoing edges from it, right? And see if any of these destination vertices, if going to them through this vertex has a lower cost than its existing path. And for U and X, previously the cost is infinity, right? Because we don't know any path to them just yet. So for both of them, coming from vertex S has a lower cost than 10 and 5. They're lower than infinity. They're smaller than infinity. So we update the total cost for both of these vertices, and then we remember, yeah, we can reach U and X from S, and then we put these two paths in the list of partial paths. Now we're going to repeat the process with the vertices in partial paths. So again, we find the vertex with the lowest cost in vertices that are in partial paths, and in this case is the vertex X with the cost of 5. So we know then for X the shortest path has been found, because if we go through any other vertex, I mean, those would have higher cost, even if they eventually reach X. Then we look at all the outgoing edges from X. Okay, there are 3 of them, and then we check each of the vertices reachable by these edges and check their cost. So let's look at, for example, the vertex U. It used to have a cost of 10 if we go directly from S. Now, if we go from X, then the cost to reach X from S itself is 5, and then from X, if we get to U, it's cost of 3. So 5 plus 3, that's 8. 8 is less than the old cost of 10. So we should update the path information for U. Now the total cost would be 8 if we go to it from X. Okay, hopefully that makes sense. Now the other two vertices, V and Y, if we look at V previously, it has an infinite cost because there is no path to it yet. So obviously 14 is less than infinity. So for V, we put, now the cost of going through X is 14, and it's 14 because, again, the cost of going to X is 5, and then from X to V is 9. So 5 plus 9 is 14. We'll put a 14 here, and then the same story goes for Y. Next, we'll repeat the same steps. So we look at everything that's in partial paths. We find the vertex with the lowest cost. And in this case, it's Y. And we know then for Y, we have found the shortest path to it. So we mark it as such. And then we look at all the edges going out from Y, and there are two of them. And so one of them is going back to S, and we know that S already has the shortest path, so we don't bother with this edge. And then for the edge going from Y to V, now remember V used to have a cost of 14. Now going through Y has a cost of 7, and the edge from Y to V is 6. So the total cost going through Y to V would be 13, and 13 is obviously less than 14. So this is a better path going through Y to V. So we update the cost for V to 13 and update the front vertex to Y. So again, we'll repeat the process. We look at all the vertices that's in partial paths, and we see that vertex U has the lowest cost, and we know that we've found the shortest path for U. So we remove U from partial paths, and then we look at all the edges going out from U. Well, it goes to X, but X the shortest path has already been found, and then we can look at the other edge of U going to V. Now the cost of going to V through U is going to be 8 plus 1, and that is 9. Previously, the cost for U is 13, so going through U is a better path. So we update the information for V, so the total cost is now 9, and it's going through U. And we'll repeat this process one last time, but it's easy because there is only one vertex left in partial paths. So that must be the one with the lowest cost. We remove it from partial paths, and that's it. We are done because partial path now is empty. Now this table shows the shortest path from S to all the vertices. Right now, in order to find the shortest path from S to a particular vertex, such as V, then looking at this table, we kind of go backwards. So we know we can get to V from U, and then we look at U, we can get to U from X. We look at X, we know we can get to X from S. So we kind of go backwards, V, U, X, and S, and that would be the shortest path, and we know the cost is 9. All right, I hope that makes sense. And now to verify that you understand it, you can use the same graph, but let's find the shortest path starting at vertex U. And just assuming that you've done it, here is the answer that I come up with. So please check this against your answer. And then here is one more exercise for you. This is a different example that I found on Wikipedia. So you please do go through the same exercise, and then you can verify your answer on with the one on Wikipedia, which I think should look something like this. And we've claimed that Dijkstra is a form of breadth first search. And hopefully that now that we've gone through how exactly it works, you can see that it does look at all the vertices in order of increasing distance. And therefore, that's just BFS. If you're not entirely still not convinced, then you can look at the illustration here, which again I found on Wikipedia. And in this particular graph, all the edges have the same weights, and you can see kind of it looks like a wave front that just moves away from the source, the starting vertex, and that kind of again demonstrate the fact that Dijkstra is a BFS.